Hi, this is Phil Newman from Longevity.Technology, and I'm joined today by the CEO of Mitrix, Tom Benson. Hey, Tom, how are you?
Hey, very good. Nice to see you, Phil.
Well, Tom, you sent a very intriguing press release to us last week, and it talks about planned trials for a fountain of youth that's targeting 130-year lifespans for astronauts. So that got our
Yes.
attention.
Yes.
So tell me, what's this all about?
Well, and as you know, because we've done some prior interviews and talked about mitochondria. That's our work is in mitochondrial transplantation, and specifically what I'm now calling mitochondrial restoration, which I think is the most accurate term.
Hmm.
And briefly, the idea is that as we age, one of the reasons that we age and one of the primary problems or primary causes of aging is that as the years go by, our mitochondrial DNA get damaged and accumulate what you would call transcription errors. Okay, and that's basically unstoppable, and the body fights it and fights it for years, but eventually by the time, even if you do everything right, by the time you're 90, 95 years old, right? We get old and that's the end. So,
So, yeah, but this conversation is going to toggle between aging diseases for regular terrestrial-based human beings as
yes,
well as astronauts, right?
yes,
So,
yes.
so let's talk about the astronauts and the implications of space travel on their bodies.
Oh, great. So, yeah. So this came to our attention about a month ago when we did a webinar on this, where we talked about astronauts and space travel and learned all kinds of fascinating stuff about radiation, zero G, the stresses, the lack of sleep, and so forth, but especially the radiation. It really is an aging, premature aging. Okay. Now,
Hmm.
premature aging happens to a lot of people. It's not just astronauts. I mean, there are children who are born with premature aging diseases and they don't live more than a few years. Okay.
Yeah.
So premature aging is a part of the human existence. But astronauts are an obvious example where people have chosen to take that risk, in
Hmm.
addition to just all the other risks involved.
So
Because,
the first users of this therapy in the trials that we'll be talking about in detail today, these
yeah.
people aren't astronauts. Is that correct?
Well, no, not quite. The target is to treat astronauts.
Hmm.
However, the initial first four trial people are just volunteers
Right.
who have basically said, we're willing to volunteer to try this before we take it to the astronauts. Okay.
Got it.
But the
So
astronauts are our target for treatment.
understood. So let's talk then about the treatment. So you're talking about mitochondrial restoration, accelerated healing as one of the
Right.
terms that you were using in your release. And I also saw that you would be potentially adding 10% to the mitochondria. So maybe you could just explain really what this is all
Right.
about.
Well, yeah. Once again, the as we age, our mitochondria become damaged, and we lose them. Um, and we lose as much as, I think, 30 or 40% of our
Hmm.
mitochondrial DNA by the time we're in our, let's say, our 80s. Okay,
Right.
and that means less energy. That's what causes aging. So our solution is very simple. We're just going to fill you back up. If you've lost 40% of your functioning mitochondria in your body, we're just going to fill it back up again.
Right, and presumably, Tom, that's something still very much to be proven. But you must have a theory sitting underneath this that if you're topping up my mitochondria, for example, I'm in my mid 50s. If you're in a position where you've topped me up and there's been a natural process of rejuvenating my own mitochondria naturally in my body, are you seeing that some of those introduced mitochondria are going to become identified by my body as younger state, and therefore my body will replicate them at a younger state rather than my, let's say, 80-year-old mitochondria?
So if your body right now has a mixture of functional and dysfunctional, it's really black. I think it's really black and white.
Uh-huh.
And so as you age, you have more and more dysfunctional and less functional. So it's a ratio. Okay.
Yeah.
It's almost like shades of gray. And so what we're trying to do is push that ratio back towards the younger state, which means we're just putting in more functional mitochondria. Okay?
Right, right. So to sort of draw a parallel, I mean, I've had platelet-rich plasma therapy, which is, which is something that at the time I had my blood drawn, I had the plasma taken out of the blood, I had it re-injected into my body. There was a mild benefit that I noticed for a period of time. I guess it felt like it tailed off quite quickly. So what would that be in the case of mitochondria? You top me up, you rejuvenate me. Is this something where you expect this to happen over, to feel the benefit over a period of time, maybe months to years? Or is this something where you still don't know whether it might take, half an hour for it to start degrading?
Yeah, that's a good question. So right now in the animal tests we're doing, which are mostly in mice, we're finding that we've gotten up to the point where we can put in about a quarter to 0.5% of the body's mitochondria per treatment. Okay, which is a huge amount, by the way. And this is what we've been working on for the past 3 years, is figuring out how to get more in there. Okay,
yeah.
So you figure I want to get anywhere from 2 to 10% boost. We don't know yet what's going to have the beneficial effect. There'll be a certain threshold where you will suddenly have more energy. And when you have more energy, your cells have more energy, which means that they can do their jobs, which means they can dispose of waste products. Your neurons have more energy. Your muscle has more energy. Okay.
Right.
And we don't know yet if that will cause, we've seen in animals that it has caused reversal of aging phenotypes. We've seen muscles grow. We've seen them get stronger. We've seen their cognitive processes improve. We've seen their immune systems dramatically improve. So I'm hoping that'll happen in human beings.
Okay, so your humans are Jeff, Gale, Ed, and Ellen, right? So they age between 75 and 80 years old. Now, obviously, they're volunteers. They've got their eyes wide open, I'm sure, as to what they're stepping into in terms of the early nature of this therapy. Let me just ask you, Tom, are you expecting for them to experience a systemic rejuvenation, or are you targeting particular aging conditions that they've got as individuals?
Good question. We're going to start with something very, very, very slow and simple, which would be skin injections, almost like allergy injections, because we want to see. I mean, if we inject in the skin, are we going to see damage? Are we going to see blisters? I mean, these are all things that you do to make sure it's safe. And then we'll slowly progress that to bigger and bigger and bigger. And eventually we would like to, the goal is to do systemic injections. And a key part of using human volunteers, we want to know what it feels like. And that's something that, and this is a problem with animal trials. They can't tell you what it feels like. Right. And that's very important. Okay. The human element is critical for this.
So, Tom, I did actually, because you did get my attention. So I was tracking some of this story on LinkedIn, in fact, and somebody asked you about the actual process of the therapy, and you were quite sort of like, this is actually not that complicated. Right. It sounds complicated. So maybe could you just talk us through the production of the mitochondria and then how they're introduced and how they're targeted?
Well, one thing I just want to say when I say it's not that complicated, first of all, you talked about doing PRP therapy. Well, PRP therapy is mitochondrial therapy. Okay.
Right.
In my perspective, because platelets are one of the biggest sources of mitochondrial transfer in the body. So when you're taking platelets out of your blood and injecting them, let's say, into a joint, you're literally moving your mitochondria over into some place you're trying to heal. Okay. Same thing with stem cell therapy. Stem cells are primarily mitochondrial donators. So when the people fly off to Panama or Thailand or wherever to get stem cell therapy, they're getting a mitochondrial therapy. So that's what I'm saying is this is nowhere near as new as it sounds. The difference is that what we've done is we've identified the piece of that puzzle that is the critical part. And then we're amplifying it dramatically. And we're doing much. It's not enough to take it out of your blood and put it back over there because you're not really changing anything. You're just moving it. We're talking about increasing. Okay. So you were looking.
Just Tom, to interrupt you. So let's talk about then the fermentation processes. So presumably either from myself or a similar type donor, you are taking mitochondria, you're fermenting them. So therefore you're optimizing them in some kind of way to make sure that when they return to the body, they are ready for prime time?
Correct. And there's actually, it is quite simple in theory. In reality, there's a lot of very tricky, incredibly tricky biology going on. And that's what we've been researching at our labs. But yes, we grow it in a bioreactor, and it is literally a stem cell bioreactor. Mitochondria don't grow by themselves. They have to be grown inside cells. Yeah. So we grow stem cells in a big bioreactor. We pull them out, we extract the mitochondria, we put them in a coating or some kind of carrier, and then we either inject them under your skin or into your intravenous. And we've talked about doing it into the eye. There's all kinds of ways to get them into the body.
So just, I mean, you're very relaxed about it all, Tom, which is admirable. But I mean, just talk us through how you extract the mitochondria from a cell.
Okay, so, and this is something that's not even new. I mean, people have been doing that for decades. You take a stem cell or any kind of cell, really, and you put it into what's called lysing, which is where it breaks down the cell wall. Mitochondria float out, and there are various tricks that many scientists do this. You centrifuge them, and the mitochondria are separated, and you get a certain percentage. We actually published a protocol of how to do this using platelets. We published that protocol a year and a half ago, and anybody can do it, really.
Right. Interesting. Well, Tom, let's talk then about the trials, because I noted that you were maybe going to be performing the trials either in Japan or perhaps leading regenerative medicine clinics that are, let's call them offshore, right? So, I mean, are you in discussion with regulators in Japan on this?
We are just starting that process. Yes, we have hired, one of our executives actually has a huge amount of experience doing that. We've talked to some teams in Japan. There are universities who are interested in jumping in. So it's actually quite doable. A lot of stem cell companies go to Japan. It is extremely rigorous science. It's very well done. They have excellent facilities. So,
yeah. Well, it's interesting to me, obviously, because the longevity field is, of course, always having discussions with itself about regulatory pathways and so on. Right. So, I mean, are you finding that really the Japanese government are kind of in their profile more open to these types of therapeutics? Why did you choose Japan? I guess is the question that I'm interested in understanding.
No, that's good. Very good question. The reason we chose Japan is that in Japan, if you get through what's called phase 1 tests, which are the safety tests, that they have a process there which is sophisticated and takes some effort to use. But they do have a process where you can start basically treating patients, and that the patients will do self-reporting of the results onto some kind of website, and then it's more of kind of a crowdsourced approach to the regulatory question of efficacy. Okay. So we do safety very, very carefully, but once it's proven safe, then they say, okay, well, you can try it for all kinds of things, and let's see what works. And
that's fascinating. And I guess if that doesn't work out, then you're going to be going offshore. And I guess the thing that happens with my mind in asking about offshore is does that put a sort of reputational risk around what it is that you're doing, going out of a regulated environment?
We're not going to go offshore to someplace that is sketchy by any stretch. Not. But I mean, there's a lot of good medical facilities all over the world, and it's not that we don't want to do this in the United States. It's just that the United States right now it's a struggle to get through some of these early phases, and it's also a very, very big market. And we also are cognizant of the fact that it's going to take time to scale this up.
Right. So then in terms of the trial, you mentioned that you've got your oversight committee. So I guess that they're going to be looking at this from not only a safety and efficacy perspective, but also what the trial's objectives are and how you're going to prove that out, right? So so you've got patient self-reporting, which is great. You're going to get some let's say you're going to get some qualitative responses rather than the quant responses to that. But how are you going to quantify success here, Tom? What are the metrics you're going to be looking at?
Okay, so that in fact is the biggest question: is how do you prove it, right?
Yep.
And I don't know if you're following the Evolution X Prize, but we've been listening very carefully to what they're working on. And the biggest question is, how do you have a judging contest where, what's the difference between taking an 80-year-old and just making them healthier by giving them a lot of exercise and better nutrition? You can
Mm-hmm.
claim making them younger, but in our book, that doesn't really qualify as making them younger. Okay. To
Yep.
us, younger is that you're fundamentally changing their cellular and genetic structure and moving it backwards 30 years, which is a
Right.
complete.
How will you be measuring that? Because I guess that is
That's
the
what
question, not for you, but everybody, right?
that's what the oversight committee is really, that's their main job,
Mm-hmm.
is to be the judges. They are the judges, okay? And it may well be that they just do it based on appearance, based on working with people individually. I mean, some people have told me they think that actually appearance and skin tone is probably the best possible measure of true aging. I know
Yeah.
there's a lot of people working with biomarkers. There's a lot of people looking at things like heart rate and blood pressure, but the problem is all of those can be changed without changing your age. Okay.
Mm-hmm.
Those can just be improved by making you healthier. So those are not necessarily reliable.
Well, I mean, will you do parallel studies with some of the other biomarkers that are out in the marketplace? I mean, obviously, we're very aware of DNA methylation and other methods of measuring age, albeit that they're all still at kind of 2.0. And there's probably a long way to go till we will get to an acceptable 5.0. But I mean, are you going to be using those as well, just to kind of help people understand?
Yeah, absolutely. We're going to have tremendous amounts of data tracking. And I want to mention, by the way, that one of our main advisors is probably the leading authority in the world on doing that kind of high level, massive tracking of the body's systems.
Mm-hmm.
And this is another reason why we want to work with astronauts, because astronauts that's exactly what they've done. They send them up into space and they look at their physical condition when they return. There was a case where they took two twins. One went into space and the other one didn't, and they did the twin study. So, we'll be doing a huge amount of measurement.
Okay, well, I mean, obviously, I'm going to come back to the astronauts in a short while, if I may. But let's just talk about why you've decided to go straight to human, right? So obviously, you're going to have four participants in your first wave. You're going to go through a lot of learnings there, probably some of that's going to be a mix between qualitative and quantitative responses from people. So you're going to hit a wall of skepticism, and there's probably going to need to be a very clear definition of what the phase 2 trials are going to start looking like. So why are you not participating in large primate studies, for example, to start off with?
Well, we've talked about this at great length, and we became very clear on the fact that doing primate studies, for example, it actually doesn't help us, because human beings are so different from other animals. Every animal is tremendously different. Mice don't age like anybody else, right? So we do all these mouse studies, but what good does it do us? Because they're different. So you could do mouse studies for the next 15 years. You're still at a certain point, you have no choice but to go into humans, and you're going to have to start from scratch anyway. Okay.
Mm-hmm.
And so, doing primates is ethically, there's a lot of problems with that. It's incredibly expensive. They don't tell us a lot of the things we know. They won't be able to tell us. And I also want to point out, mitochondrial transplants already being used in humans already. Yep. It's just not being used for aging. It's being used for other rare diseases. So it's not like we will be the first by any means to do it in human beings. Other people have already done that.
So, Tom, in your materials, you talked about an in-vehicle radiation-hardened mitochondrial bank. So that got my attention. So we're assuming that this is going to be something on the payload of a space transportation vehicle, whatever it may be, whoever the manufacturer may be. So talk me through that. This is presumably a way for the onboard astronauts to replenish their mitochondria.
Right. So let's say that you are in a moon colony for a month, or you're traveling to Mars, and that's a 6-month trip. Okay. Let's say there's a solar storm and the radiation, we get a huge radiation dose, which is a very big danger. Okay. Or let's say you're on the moon and you just fall down. Okay. Turns out I never knew this. That's very easy to fall on the moon because you're not balanced. It's hard to balance. So let's say you break an arm or you get a big scrape or you get a burn. Okay. Those people are, we've spent billions of dollars to send them there, and they need the best medical treatment they can get, and they need it on an emergency basis, certainly for radiation. So mitochondria have an advanced accelerated healing property. So if I could smear mitochondria on a burn on my arm, what the early research has shown is that can cause rapid healing. Okay. If I have a radiation, if I get a big radiation dose and I get sick from that, I mean, mitochondria are known to be affected by radiation. So if we replace them with healthy ones that we've kept inside this bank with lots of radiation shielding around it, then presumably we could help those people, recover from that.
So let's say there's a crew of 10 people, and that mitochondrial bank has got the mitochondria in there. Would there be 10 different compartments, each tailored to each of the astronauts, or would there be a level of generic access to generic mitochondria?
In the future, we're hoping to go to generic mitochondria, but I think that certainly for a space trip where you're spending that kind of effort to prepare for it, I think you would create what we call autologous mitochondria for each of the people. And the way we envision it is there would be multiple types of mitochondria. There might also be stem cells. There probably would be some growth factors, maybe some extract of platelet-rich plasma, which has a lot of healing properties. And that would be all stored in a cryogenic thing. And then, you have some very powerful equipment to tell the astronaut how to dose themselves or how to treat themselves.
So in the case of Dosage, Tom, presumably, there's going to be a point where there's going to be a regular therapy, we would hope, for astronauts to take, so that obviously you're making sure that they perhaps age at the rate they would do on Earth. So presumably this is where you're going with the theory of all of the work that you're doing, that it's not just about fall over on the moon and you can fix yourself quicker. It's about being able to stop the clock, as it were, for astronauts as they're going on these large missions.
Exactly. And so from our perspective, from the mitochondrial perspective, the healing and aging are actually two sides of the same coin. Okay. I've always thought that. And so if we can use a small amount of this stuff to help save them from some injury or help them recover or heal or so forth, then we can use larger doses in much larger quantities to slow down the aging clock, and I think even potentially reverse the aging clock. Okay.
Oh, yeah. So, well, fascinating, Tom. So, there's going to be a few bumps in the road before you get to being on the top of the next SpaceX rocket. So, let's bring it back to more terrestrial terms. When are you going to get the program up and running this year? Is it this year, next year?
That the plan is to try to do it, if possible, at the end of this year. It'd probably take about a year from starting point to get through the initial regulatory paperwork. And there's lots of preparation to do. So all that is dependent on funding. And as you know, funding in the longevity field has been a challenge for the last couple of years. So, but it should be, I'm hoping, at the end of this year or early next year.
Well, of course, in some respects, the theory behind the more extreme and let's say not controversial, but the more interesting some of the therapies that are out there, the easier it is for them to attract capital. So, Tom, obviously, it is fascinating, and we wish you and your colleagues the best of luck, not only with closing your round, but likewise getting the program up and running. And keep us posted, won't you?
Well, thank you very much, and hopefully we'll talk some more again soon.
I'm sure we will. Thanks, Tom.
All right. Thanks a lot. Bye-bye.